On July 27, 2013, a newly filled reservoir in southwestern China produced a landslide roughly 200 meters wide and 250 meters high, sending an estimated 120,000 cubic meters of material into the Jinsha River and generating waves reported at more than 20 meters. The event happened beside one of China's newest megadams. But the landslide wasn't the strangest movement engineers were measuring. Inside the same project, scientists were recording something much slower. The enormous canyon itself was changing shape after the reservoir filled, with measurable movement in the rock surrounding the dam. Researchers have described the phenomenon as river valley contraction, and one published study noted that a widely accepted explanation for the mechanism was still unavailable. This is Ziluodu. And the problem isn't that the dam is collapsing. The problem is that one of the biggest concrete structures ever built was placed inside a geological system that continued moving after the water arrived. Ziluodu was never meant to be a monument sitting quietly in the landscape. It was part of China's enormous west-to-east electricity strategy, designed to take the hydropower potential of the Jinsha River and send electricity toward the industrial centers of eastern and southern China. The developer and owner was China Three Gorges Corporation, with China Three Gorges Projects Development Corporation handling engineering management. The principal designer was Chengdu Engineering Corporation Limited of Power China, while major construction work involved Sino Hydro and China Gezhuba Group. Construction began in December 2005, and the project was conceived on a scale that made ordinary hydroelectric engineering look almost small. The dam rises 285.5 meters above its foundation. It is a double-curvature concrete arch dam, meaning its shape bends both vertically and horizontally, allowing water pressure to be transferred into the mountains on either side rather than forcing the entire structure to resist the load by itself. Behind it sits a reservoir holding about 12.67 billion cubic meters of water. And underground, hidden inside the mountains, are 18 Francis turbine generator units, each rated at 770 megawatts, producing a total installed capacity of 13,860 megawatts. The first generating unit entered operation on July 15, 2013. The 18th and final unit followed on June 30, 2014. For a project of this scale, that is an extraordinary engineering achievement. Then the engineers started doing the math. Here's the thing about Ziluodu that every high dam engineer knows: the concrete is only half the structure. The other half is the mountain. An arch dam works because the surrounding rock can receive and redistribute enormous forces. In a normal building, if the ground moves slightly, the structure may move with it. At a 285.5 meter dam, movement in the foundation and valley can alter the forces traveling through the arch itself. Let's talk about what happens structurally when you fill a canyon with billions of tons of water. The water doesn't simply push against the dam. It changes the stress conditions underground. Water enters fractures and joints. Reservoir levels rise and fall. Pore pressure changes, meaning the pressure of water inside tiny spaces in the rock can reduce the forces holding fractured rock surfaces together. At the same time, the immense load of the reservoir changes the deformation of the surrounding geological mass. That combination is called hydromechanical coupling. In plain English, the water changes the rock, and the changing rock changes how the water moves. At Ziluodu, researchers found that the rock mass around the reservoir experienced a continuing contraction after impoundment. One major study analyzed monitoring data from 2012 through 2021 and found a significant, continuous river valley contraction upstream and downstream of the dam. By May 19, 2017, one monitoring line near the dam crest had recorded 62.45 millimeters of valley width deformation. Not slightly. Not as a design flourish. More than 6 centimeters. And another study examining the entire deformation pattern reported an accumulated horizontal displacement of about 52 millimeters at the dam crest after 4 reservoir storage cycles, with the movement directed upstream. That sounds alarming until you understand what the monitoring is actually telling us. The dam was designed for movement. The engineers installed extensive systems to measure it, including geodetic instruments, non-geodetic deformation sensors, thermal monitoring, and internal structural measurements. They weren't waiting for the mountain to reveal a problem. They were watching it move millimeter by millimeter. But here's something about this building that nobody ever explains. The engineers weren't dealing with one simple foundation. They were dealing with a fractured rock mass inside a steep canyon, with geological structures, seepage pathways, and changing water pressures interacting across a huge volume of rock. The foundation was excavated and treated specifically to improve its behavior. Research into the foundation design describes the use of consolidation grouting and adjustments to the excavation surface so the dam and foundation could work together more effectively. And then there was water. Studies of the dam foundation have documented seepage and leakage behavior, including a measured maximum leakage rate of about 192 liters per second in the plunge pool area after impoundment. Researchers traced different components of that water to groundwater, reservoir water, and downstream sources. That part doesn't make it into the architecture magazines. Because this isn't really an architecture problem. It's a rock, water, and pressure problem. And the more interesting detail is that the deformation wasn't simply downward settlement. Researchers found uplift in parts of the dam base and downstream bedrock, with measured maximum uplift reaching about 60 millimeters in downstream bedrock in one analysis. The overall deformation pattern was unusual compared with the more familiar settlement behavior seen at other large dams. Think about what that means for a moment. The canyon was not behaving like a rigid bowl. It was adjusting. And then came the earthquakes. After the reservoir began filling in May 2013, seismic activity around Xiliuadu increased significantly. Two notable events reached magnitude 5.1 on April 5, 2014, and magnitude 5.2 on August 17, 2014. Researchers have linked the largest events in the area to stresses associated with reservoir impoundment, while other studies have found that the earthquakes did not threaten the dam's safety. The April 5 earthquake struck at about 6:40 in the morning. At least 10 people were injured and several houses collapsed in the affected area. The epicenter was reported about 13 kilometers deep near Xiliuadu township. Nobody needed to be inside the dam for the geology to make itself felt. But that is not the remarkable part. The remarkable part is what happened inside the engineering data afterwards. The researchers kept measuring. Satellite radar has also been used to monitor deformation around the Xiliuadu reservoir, including horizontal and vertical movement between 2014 and 2019. More recent INSAR research has continued to identify deformation zones along reservoir banks while finding most residential areas around the station relatively stable. Compare Xiliuadu with the Three Gorges Dam. Three Gorges is a massive concrete gravity dam, relying heavily on its enormous weight and foundation system. Its foundation contains joints and geological features that were specifically analyzed for sliding stability. Compare it with Vagent in Italy, where geological movement above a reservoir became catastrophic. Or with Malpasset in France, where foundation and geological conditions contributed to a completely different kind of dam failure. Here is the fundamental difference between Xiliuadu and every other megadam we've covered. Its most interesting story isn't a collapse. It's controlled movement. The dam is still operating. China Three Gorges Corporation reported more than 4,000 consecutive days of accident-free production by October 2023. But here's the question that sits beneath all of this. How does a structure designed to last for generations behave when the geology beneath and around it continues to adjust? Concrete experiences creep, meaning it slowly deforms under sustained stress. Rock can also deform. Fractures can open or close. Seepage pathways can change. And the reservoir itself rises and falls. At Xiliuadu, researchers have modeled the interaction between stress, deformation and seepage, finding that the measured behavior could be reproduced closely by coupled models. One study reported model-to-measurement agreement with our superscript 2 values greater than 0.98. That's reassuring. But it doesn't erase the unusual part. The same research says there was no widely accepted scientific explanation for the complete river-valley contraction mechanism. That is an important distinction. The engineers can measure the movement. They can model it. They can track its relationship with reservoir levels and seepage. But understanding every part of why a huge geological system moves the way it does is harder. There is no historical data for what a 285.5-meter arch dam looks like at 50 years, because no Xiliuadu dam is 50 years old. It is the first. It is the only one. In 2040, engineers will have more than 2 decades of operational data to examine. In 2060, another generation will be able to compare deformation, seepage, seismicity, and concrete against a much longer record. And in 2075, the people reading those inspection reports won't care how impressive the dam looked when it opened. They'll care about millimeters. About cracks. About pressure. About whether the movement slowed, stabilized, or continued. That's how infrastructure ages. Not dramatically. Quietly. Meanwhile, the human reality is remarkably ordinary. Electricity continues moving east. The turbines continue turning. The underground powerhouse still does the job it was built to do, while the reservoir stretches for roughly 204 kilometers through the Jinsha River Valley. A worker can stand inside the cavern, surrounded by concrete and machinery, and hear the low mechanical vibration of a 770-megawatt turbine operating somewhere beyond the walls. A maintenance engineer can read an instrument showing a fraction of a millimeter of movement. A satellite can pass overhead and measure deformation across terrain that looks completely motionless from the ground. And here's the detail nobody surfaces. Most people using the electricity produced here will never know any of this happened. They'll switch on a light. The light will come on. None of them are thinking about the rock beneath the reservoir. Right now, somewhere in eastern China, someone is using electricity generated hundreds of kilometers away by water pressing against a 285.5-meter wall of concrete, while sensors continue recording the slow adjustment of the mountain around it. No collapse. No abandoned project. Just a giant structure, functioning exactly as intended, inside a geological system that refuses to remain perfectly still. And perhaps that's the most honest way to understand Xilhuadu. Not as a dam that is failing. As a dam that is moving, because everything around it moves too. Drop it below. Would you trust yourself to stay here knowing what the instruments are measuring? See you in the next one. Verify. Xilhuadu Dam/Xilhuadu Hydropower Station, Jinsha River, China. China Three Gorges Corporation, developer and owner. China Three Gorges Projects Development Corporation, engineering management. Qingdu Engineering Corporation Limited, Power China, principal designer. Construction began December 2005. Dam height, 285.5 meters. Dam type, double curvature concrete arch dam. Reservoir capacity, approximately 12.67 billion cubic meters. Generating units, 18 by 770 megawatts. Installed capacity, 13,860 megawatts. First generating unit, July 15, 2013. Final generating unit, June 30, 2014. 2013 Huangping Village landslide, approximately 200 m wide, 250 m high and 120,000 cubic meters. Reported waves exceeded 20 m. River valley contraction monitored from 2012 to 2021. Valley width deformation, 62.45 millimeters by May 19, 2017 on monitoring line VDL04. Accumulated dam crest horizontal displacement, approximately 52 millimeters after 4 reservoir storage cycles. Maximum downstream bedrock uplift reported, approximately 60 millimeters. Maximum reported plunge pool leakage, approximately 192 L/s. Magnitude 5.1 earthquake, April 5, 2014. Magnitude 5.2 earthquake, August 17, 2014. April 5, 2014 earthquake, at least 10 people injured, several houses collapsed, epicenter reported about 13 kilometers deep. More than 4,000 consecutive days of accident-free production reported by October 2023. Reservoir length, approximately 204 kilometers. The 2022 engineering geology study reported no widely accepted scientific explanation for the complete river valley contraction mechanism. Story end. Please subscribe my channel.